figure out how much of the square, the big square, is taken up by the red, taken up by the green, taken up by the yellow.
I'm sorry, Kate. It's massive. Don't hit me.
Okay?
Would they all be the same?
Andre, did you get a haircut?
Yes, they are all the same, aren't they?
Yeah, so you only
What are we trying to figure out? Just like, don't pay attention.
How much of the total square's area is taken up by the red, taken up by the green,
Okay.
taken up by the yellow?
1/3.
It's a good guess.
A third.
A third.
Can you prove it?
What are we trying to do?
No, I can't. You know
So what you're going to do
Because
is you're going to say the whole area is x by x, right?
okay.
Cool. So how much of the area would this one red square be? A quarter of x squared, right?
Yeah.
A quarter x squared, right? A quarter. How much would that one be?
No.
A quarter of a quarter. When we say the word of in math, we mean multiplication. So a quarter of a quarter. What's a quarter of a quarter?
2. 16.
16, right? So that bit is a 16. And so on and so forth.
Yeah. You just keep going. Seriously.
I would go out to 7 squares, because if you see it keeps going further and further, I can't zoom in any further. Right?
I can't.
But I count 7.
I only count 6.
I know, everybody says that.
Or,
There's a real itty bitty one, right?
Think about it, think about it. Song of the day is dedicated to all of you, although some of our listeners in particular. Song is Super Stupid by Funkadelic, which is a band that was formed out of Parliament, which was a band that George Clinton led for a while. It actually originally started out as a doo-wop band and then turned into a funk band. Then later transitioned to combine with his other band and create this super band called Funkadelic. Funk meaning funk music, adelic as in psychedelic. So he took psychedelic rock and combined it with funk and created this band, Funkadelic. The album is Maggot Brain. You've seen it on the screen before. It's the picture of the woman that's buried up to her neck and she's screaming. That is the album it's from. The song, again, is Super Stupid, dedicated to a special song. Eddie Hazel on guitar, and I believe on vocals. I don't want to talk about it. I don't want to talk about it. Oh my God. I don't want to talk about it. I have to walk. There you go. Keep going. I know. All right. All right, face this way. Let's talk about it. Let's talk about it. So, here we go. So, we said that we just focus on the red area. We've got a quarter of the whole area, so that's a quarter x squared, right? Because the whole area is going to be x by x. Oh, that's right. I forgot you're supposed to see it. My bad.
Oh my god.
Dude, that's nasty.
Have we never seen that before? It happens all the time.
It was
What?
an accident.
It is just like the problem.
I am now scarred.
It's a hint. It's a hint. It's a hint. It's a hint.
How was that?
But it's not going to matter because no one ever listens.
Imagine just.
So, not in this class. I just mean in general. So we have a quarter of x squared. X squared is the whole area, so a quarter of the whole dumb thing is what we're saying here. Here we have a 16th of the whole dumb thing. But if I keep going, I want a quarter of a 16th, right? This square here is a 16th itself. And so a quarter of a 16th, well, when we say of, we mean multiplication. What's 4 times 16? Well, it's the same thing as 4 times 8 times 2. What's 4 times 2? What's 8 times 8? 64. Play with your math. Okay? So that's 1 over 64. Makes it easier, right? 1 over 64 x squared. We keep going. I want to go up to 7. It's going to be 1 over something x squared. What's 64 times 4? Do it in your head. 60 times 4 is what?
No, it's not.
Nope. 60 times 4 is 240.
There we go. Wrong way.
But we need to do 64 times 4. So I need 4 more groups of 4 here, right? I've got 60 groups of 4. I need 4 more groups of 4 to make 64 groups of 4. So that's going to be plus 16. It's going to be 256 in the bottom. You dig? Okay, so now we need to do 256 times 4. Well, how about we do, instead of that, let's do 250 times 4. You know what that is? 250 times 4. 1,000. Thank you, Thomas. All right, so we really wanted to do 256 times 4, so we're 6 groups of 4 short. So, see what I'm saying here? So we need 24 more.
Didn't you just say that whole top right box was 1/4? Did you?
This top right box?
Yeah, why can't you just say 1/4?
That whole thing is 1/4, but we don't know just how much the red is.
Oh, okay.
So we got 1024 here. I've done 1, 2, 3, 4, 5 boxes deep into our box inception. I need 7 more. So we're also going to add on 1 over something else, x squared, plus 1 over something else, x squared, and then we're going to call it a day, right? Okay, so I got from here to here by multiplying by 4. What's 1,024 times 4? Easier question. What's 1,000 times 4? 4,000. Now I need 24 more groups of 4, right? Maybe you don't know how to do that in your head. What's 20 groups of 4? 80. What's 4 groups of 4?
60.
So in total 96. 4096. 4096 times 4. What's 4,000 times 4? 16,000. What's 96 times 4? Let's round up this time. Let's make it, instead of 96, let's make it a hundo. That's 400, right? But we went over too much. How much more did we go over? How many groups of 4 did we go over? By 4 groups, right? We wanted 96, but we ended up doing 100. So we got to subtract 4 groups of 4. We can do that. 16,000 plus 400 is 16,400. 400 minus 10 is 390. Minus 6 is 380. So it's going to be 16,380. Confirm or deny?
Deny. Or confirm.
84. Right, because we're minusing 16. So it's like subtracting 20 and then adding 4 back, or subtracting 10 and then subtracting 6. I don't know. So 16,384. All right, so now we just add them all up, right? We get our answer, which you said would be a third, right?
I said that.
Yeah, you did. You did. You did. You did. You would think that, wouldn't you? All right. So we need common denominators, right? Just blew her mind. All right. Yes, we do. But what if we didn't? Let's see if we don't. Let's experiment. Unhalf plus 2/3. What if we just added a cross? A cross, not cross. We don't cross multiply. A cross. We get 1 plus 2, which is?
3.
And 2 plus 3, which is? How do you know this is wrong? Because my teacher told me so. Ladies and gentlemen, I have 2 rules that you're aware of. I have said them. You just don't remember. No one listens. Rule number 1 is this rule. Trust no one.
Oh, well.
Which means if you're saying, because my teacher told me we need common denominators, then you broke rule number 1. Rule number 2, of course, is this. We've talked about this, I believe.
I don't have that.
See, you look so much different on the.
Just a plan, nothing sinister, just be aware, right? Just have a plan, just in case, right? It's a zombie apocalypse type of thing.
My plan is to drop
So we're in violation of rule 1 if you say, well, that doesn't work because I know we need common denominators, right? Why do we need common denominators? Why does this not work? How do you know this doesn't work just from looking at it?
because you can't add them that way.
Why?
But they're not common denominators.
Yeah, but why does that matter?
I guess I don't know how to.
Yeah, exactly, right? You just were told it doesn't work that way. And so what's going to happen is you're going to forget that you were told that, and you're going to do this, and you're not going to think anything about it, and you're going to get stuff wrong, right? So let's actually know why this is. That way we can actually know what's going on. What does it mean? A half plus 2/3. I know, you guys lose your frickin' minds as soon as I write a fraction down, but think about it. What does it mean? Dykema.
Oh, what?
I know, you weren't, but you are. All right, so Mr. Dykema, how do we know that a half plus 2/3 can't be 3/5? Like, there's just no way that could be a right answer.
Oh, it's something with the denominators.
Yeah, but like, why do we need common denominators? Forget about it. I don't want you to answer that because you don't know. What I want you to answer is, why can this not be 3/5? Don't tell me common denominators. That's not a reason why. That's just because someone told you so,
Because it
right?
doesn't make sense.
It just doesn't.
Why doesn't it make sense?
It just doesn't work like that.
Oh, flip on. 2/3 is bigger than 5.
We have 2 people that got him. Wonderful. No talking, no talking. Anybody else? Anybody else know the answer? Why this can't be? I mean, there's multiple ways to know this isn't the right thing. We've had 2 people say the same thing in the same row, column. I mean, why not? Who says? Okay. Can a half go into 3/5?
Yeah, they can.
I mean, 3/5 is slightly bigger than a half. Is that what you mean? It doesn't fit in like perfectly, but we're talking fractions, so nothing really does, right? But,
Excuse you.
got it.
That's disgusting.
Peak comedy. All right. So we have 2 people that have figured out one reason why this can't possibly be the right answer. Come on. Come on.
2/3
Shut up. Listen.
2/3 bigger than 3/5.
2/3 is bigger than 3/5.
Okay.
How do we take something that's already bigger than 3/5, add something more to it, and then end up with a smaller number? Brilliant. That's not what you were saying. What you were saying is, look, 2/3 is bigger than a half, and a half plus anything bigger than a half should be bigger than 1. That ain't it, Chief. Right? That's what Caden was saying as well. So it doesn't work that way. Oh, okay. I'm sorry. I won't. All right. So when we're going to add these up, we need common denominators.
The 4 sees the 4.
Okay, I understand. So now, a quarter x plus all this stuff, right? It's going to be something x squared at the end of the day. Let's just ignore the x squareds for now. We need to add a quarter all this stuff. So what's going to be our common denominator? What's going to be our common denominators? Or actually, you know what? Let's go back a little bit. I jumped the gun. I'm assuming, and I don't want to do that. So let's do it the right way. Unhalf plus 2/3. We need common denominators. Well, what we need is those bottoms to be matching. Right now, we're talking apples and oranges here, okay? We're talking chickens and ducks. We're talking, I don't know, bologna sandwich and Batman signals, okay? 2 different things. So we need to be talking about the same thing. The way I think about denominators is they're like units. Like, I've got 1 chicken here and I've got 2 cows there. Add them together doesn't work. I'm sorry, are you okay?
No.
No? Will you be okay?
No.
Okay, would you like to go take a break?
No, it's fine, just go.
Okay. So we need common denominators. We may be talking the same things, apples to oranges, okay? So, how many thirds are in a half? How many halves are in a third? It's not going to be nice, right? But if we talk about 6, that's something they have in common, right? How many sixths are in a half? 3 sixths, right? 3 out of 6 is half. How many sixths are in a third? A single third?
6.
A single third. You're jumping the gun. A single third.
2.
2 of them. So how many sixths are in 2 thirds?
3.
Try it again.
4.
4 thirds.
4,
6.
I don't know.
2 out of 6 is a third, right?
Yes.
So 4 out of 6 is going to be 2 thirds.
Alright.
Right, it's double.
Yeah.
You see what I'm saying here? Okay, so we have 7 sixths in total here. And again, think of it like a unit. You have 3 sixths, I have 4 sixths, together we have 7 sixths. I have 3 chickens, you have 4 chickens, together we have 7 chickens. Chickens in this analogy is the 6. I use chickens because you are from Butt Scratch, Illinois, and everyone knows what a chicken is. Yeah?
Butt scratch Illinois.
That's right, and I say it affectionately. All right, so 7 sixths, which is bigger than 1, which is what we would expect when we have numbers that are bigger than a half being added together. Whoa, I don't. So 7 out of 6. So let's get common denominators here. So, common denominators here. How are we going to do it? All right, if I just have these two and I wanted to add them together, what's the common denominator I would get? 16, very good. If I just had these, what's my common denominator? I know, we're feeling super edgy. Can we bring it back? All right. What about here? What would our common denominator be? 256. So if we're here, what would our common denominator be? All of them are going to be out of 16,384. How many of them do we have? We are 7 squares deep. All right. So, well, one of them is just going to be 1 out of 16,384, right? Cool. How many 16,384ths are in 1 out of 4,096?
Run that. Should we do it in a small scaled version?
4 of them. Didn't we get from here to here by multiplying by 4? Yeah, so aren't there going to be 4 of these guys? Yeah. There's 4 out of 16,384. And then from here to here, we multiply by 4. And we multiply by 4 again. So multiply by 16, not 8. We multiplied by 4 twice. When we add 4 twice, we get 8, right? When we multiply by 4 twice, we get 16. Common misconception, happened every class. Well done. So, no, seriously, it's good that you point that out because then I get to talk about it. So that was times 4. From here to here is times 4. So now we've times 4 3 times, so it's 64, right? 4 cubed. 16 times 4, 4 cubed. What is, we do this to here, we times 4. So we got 4 times 4 times 4 times 4. What's that? 256. You see the pattern? We've already done this. The next one's going to be what?
1,024.
Duh, because that's a
We did the last one, did we?
And then 4, 0.
9, 6. Now we just add them all up, right? Which ones you want to add together? Pick 2 to add together.
The first 2.
Pressing A. Which 2 you want to add together? 1 and 4? Oh, that's adorable. 5. Well, you've done it. You've done it. I would have added those with some bigger ones to kind of make the bigger ones easier, but you just made the little ones as easy as possible. That's a fair scenario. I'd try to balance it out a little bit. Brainerd, which 2 you want to add together?
Let's go. 64 and 256.
All right, let's add them up. What's 256 plus 4? Brainerd, eyes up here.
Sorry.
It's all right. 256 plus 4 is what?
260.
260? 260 plus 60.
3, no. Is it 320?
320. All right. Autumn. Which 2 you want to add up? We've got 3 options. She took your easy ones away. you want to add up 16 in this, 16 in that? Yep, we got to add them all up.
Oh,
You could have done these two if you wanted to. Would you rather add those two together? Yeah, okay, cool. It's your choice. All right, so these two. Let's add them up. What do we get? We get about 5,000 here, right? Okay, so that's 5. 24 and 96 we can do in our head. So what's 96 plus 4?
10.
Nope. Listen to what I'm saying. You're not wrong, but you're also not right. 96 plus 4. 100, even, right? And then add 20 more. 120. Cool. Lastly, the odd man out for this one was 16. It almost got picked, but it didn't. All right, so now we got to add all these up. Okay, 5 and 6 is 1. Carry the 1. We get 3, 5, 6 down there. And then we get 4 here, and we get 5 there. 5, 4, 6, 1. Confirm.
sure.
That's what they always say, and they regret it. 5, 4, 6, 1 over 16,384. All right, so Rosie said it should be a third, right? That's the red area right there, all in total. Does that actually equal a third? Get out your calculator, plug it in. See?
Just divide them by each other.
Yep. Mhm.
Keep dividing them by.
All right, pause. Boring. Too long. When something reduces to a third, it should be divisible by 3. Is this divisible by 3? 5, 4, 6, 1?
Add up.
We get 9 plus 7, which is 16. 6 plus 1 is 7. Is it divisible by 3? Uh-oh. So why isn't this a third? We have equal areas for the red, the green, and the yellow. 3 colors dividing up the square into 3 pieces, 3 equal sections. But it ain't a third. Huh?
Wait a minute. Don't you just say that's
Immediately after saying something. Nothing!
The green's different. I don't know. Come on, Haley.
Why isn't it a third?
I don't know.
Is it close to a third? Great question.
Hang on, stop.
3.
Me?
Yes.
Okay, I'm standing still. Why?
Okay, no, it doesn't because the denominators equal 3, like anything divisible by 3. Yes.
So it's not a third, but it could be really close. Is it?
That's 22.
Let's try to reduce this. Turns out 5, 4, 6, 1 ain't prime, neither is 16, 3, 8, 4. This is maybe simplest form, but maybe not. I don't know. What is 5, 4, 6, 1 divided by 13? Let's do that in our head. Okay, I'm trying to get to a common divisor here. Okay, 5, 4, 6, 1. Let's estimate that. Okay, 13 is how many is a number that I'd like to use, and I'll show you why. I realized this early this morning, and now I have to do it. 5, 4, 6, 1. We're gonna divide that by 13. So give me an estimate. 13 times what do you think would be about 5, 4, 6, 1? 45? Give me a nicer number for an estimate. If we're gonna estimate, might as well make it nice, right?
47.
We could be a little bit nicer. Let's try a hundo.
Yeah, Haley, be nice.
Too small, which means 50 was too small, which means 46 was too small, which means 45 was too small.
150.
All right. Let's do 200. Still too small, right? It's okay. We're getting closer.
500.
500. All right. 50 is what we get here. 5 times 10 is 50. Plus 15 is 65. So we get 65 with 3 zeros. 2 zeros, sorry. 6,500.
I said.
40 and 12 makes 52. Ooh.
So you didn't say that. It was well by 1. So you.
Remainder 1. So 13 doesn't go in evenly. Why did I pick 13? Well, 1, that's pretty funny, right? Did I tell you about the time I made an entire exam, 420 and 69 for the answers? It was amazing to just see it cascade about as they realized what was happening, right? They're like, this can't be it.
That would have been awesome.
This can't be it, right?
wouldn't catch on.
Stuff man, right?
Anyway, so it turns out We don't need to check every single number to see if a number's prime or not. This one actually isn't. It's a terrible example. But let's check 23, which we know is prime. We don't have to check 1 through 23 in our calculator. Does it divide by 22? Does it divide by 20? Right? We don't have to do that.
We're supposed to figure out how much of that is being.
Would you just relax? We're on a journey here.
I
Okay?
didn't pee.
All right, good. So,
Learning is confusing and
mucho cuidado, por favor. Thomas, do you have any words of advice?
Don't pee on somebody.
All right.
I got yelled at.
Gotcha.
Fat rep for me.
Oh boy.
All right, so we don't need to check every number. You can tell if a number's prime if you only check a couple. The magic that's going to happen, I'll explain later, but not today. If you check numbers less than root of 23, the number you're interested in, if you check that and none of those work, then it's prime. If you know why or can figure it out, maybe I'll give you some self-development points, but I will explain to you soon, okay? But for now, let's assume. So if I wanted to see if 23 is prime, spoilers it is, I would have to check numbers less than root 23. Now, what is root 23 approximately? It's between two numbers.
4 and 6.
4 and 6 is a better approximation.
4 and 5.
4 and 5. How do you know it's between 4 and 5? That was really good. How do you know it's between 4 and 5?
Because 25. 4 times 4 is 16. 5 times 5 is 25. Closest.
Root 25 should be bigger, right?
Oh, I remember doing this.
And root 16 should be smaller. And we know what that is. That's 4, that's 5. So this is somewhere between there. It's really close to 5, isn't it?
Like 4
Right?
and a half.
It's a little bit even closer, right? Because it's really, really close to root 25. So if we check numbers less than 5, we'll even go less than or equal to just to make sure, right? Then we know it's prime if none of those work. Okay, so 1 we can skip because obviously 1 and 23 are factors, right? Divisible by 2? No, it's not even. How about 3? No, they add up to 5. 4, no, because if it's not divisible by 2, it's not divisible by any even number. Okay, now we check 5. Doesn't end in a 0 or 5. So 23 is prime. We don't have to check any more than that. Isn't that exciting? Yes.
Can you go back to the big picture, like where we set the box?
Mm-hmm. So, it turns out that this thing doesn't come out to a third very evenly, right? It doesn't. If it did, 13 would go in nearly perfectly, and it would go into it. No, yeah, it would go into 420 times, because 420 is divisible by 3. But it ain't, so it's not a third. Why is it not a third?
Because of all that.
All what?
Because there's a tiny little box cup. So I feel like they should be a third though, because they all have equal amount of boxes for each.
Because there's no end. So, we stopped at 7 squares. But this goes infinitely off, right? I keep dividing by 4, dividing by 4, dividing by 4. So it never actually is a third until we go to infinity. And then it is perfectly a third.
But it's impossible to get to infinity, so.
If we go to infinite number of boxes, okay, then it'll be exactly a third. But if we stop short, it'll just be really close. So if I stop right here, right, if I cut this out, that's just a quarter, right? Not very close to a third. What's a quarter in a decimal? 0.25. So we get 0.25 if we stop after 1 box, right? If we go to 2 cuts, now we've got a quarter plus a 16th. Get common denominators. How many 16ths is that? 5 16ths. 4 here, 4 16ths here, 1 16th there, 5 16ths. What's 5 16ths as a decimal?
5 15s?
16.
1/3. 1/3, right?
Well, 5 15ths is exactly a third, so what's 5 16ths?
A little over a third. By like a couple decimals.
A little bit under, right? Because 16ths has more cuts.
I'm always
So a little bit under a third. It's like 0.3331, something like that. After 3 boxes, now we have a 64th here. So we get common denominators. That is 16 64ths. That's 4 64ths. So we've got 20 64ths plus 1 64th is 21 64ths. Now 20 out of 64, that's close to a third, right? 21 out of 64, really close to a third, but not quite. A little bit under, a little bit over. A little bit under. Something like that. You see how we get closer and closer the more boxes we take? We are approaching a third. Hello.
I still worry you for a second.
Yes, you may. Laura Lee? So we're approaching a third. The closer we get to infinity. And the reason for that is if we stop, right? If I stop there,
How did you just do that so quick?
Because he's made 4 of them today.
Because he's done this.
if I stop right here, right, I've got 4 boxes. I've got 4 of the green, and I've also got 4 of the yellow. But what do I have left over? This guy, which never gets accounted for. So of course it's always going to be less than a third. Because there's still more to do. Every time, it's going to be less than a third. Just underneath, because there's still a little bit more we got to account for, right? And we go again, and again, and again, and again, and right, we get closer and closer to a third, because there's less and less to account for.
How many times do you think you'll take for you to get that?
To get to infinity, infinity times. It is an idea, which means we can never actually get there, but if we did, then it would be exactly a third. And it has to be exactly a third, right? If we have the same area for 3 different things, that's going to be a third. Doesn't matter how I arrange them, right? If I did this, you would not argue with me. That's a third, that's a third, and that's a third. Not drawn to scale, right? But a third is 0.3 repeating. How can it be that if it has to go on forever? Well, it can because eventually it would get there. Sort of, not really. Yes.
I have a question. I feel like you just explained it, but
It's okay.
like
Haley, I swear.
you know how there's like
Oh my God, we're so
there's 3 different colors, you know,
Mm-hmm.
and there's an equal amount of boxes for each color. So how could one color not be 1/3 of the square? You know what I'm saying?
It is actually 1/3 of the squared if you keep going to infinity, because then it will be that way. But if you stop at any point, Thomas, if you stop at any point, like if I stop right there, notice how we've got red here, 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 and here. We've got green here, 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 and here. And we've got yellow here, 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 and here. But we have that little square at the top there that still needs to be accounted for. And there will always be one little square left over, right? Unless we go to infinity, which is an idea, not a number. But you can go to an idea. Let's go to Pizza Hut. I'm sorry, that's a number? Or an idea, not a number? We can't go. Right? What's your favorite number? Pizza Hut. All right, put that away. Here's what I want you to do. Take out a piece of paper. Draw me a picture. I want 2 parallel lines. That's totally parallel. And I want 1 transversal cutting them. Sounds like a wrestling move, but it ain't. Transitive property, everyone's touching everybody. Put it away. I used to do a thing, if you got an A on all of your quizzes, you get to have your phone out as much as you want. Everybody else had to give up theirs as they didn't get A's. But I felt that was demeaning. But really, like, that should be how you do it, right? Like, if I can handle it and pull up an A with my phone out, then keep doing it, bud, right? But if you can't, like,
did you put the
don't do it. No, because I got locked out on Friday. They changed the locks on me. So some of you guys are like, yes, thank God he didn't put them in. Others of you are like, please, God, put them in.
Well, I don't really know yet.
That was a very interesting face. I don't really know yet. That was great. That was like a meme.
Shut up!
Yeah.
Draw this! Oh, Miss Carpenter. All right.
Yeah?
Yeah?
Like these
Okay. Just don't hurt me.
Oh, this is what we did Friday. Exactly what we did Friday. Not exactly what we did. The numbers are this is our homework.
It's not here.
I'm not kidding though.
This is our homework.
Pretty much. All right, so nerds. We know that if 2 lines intersect and they're cut by another line, we call that line a what? A transversal. If the lines are parallel, then we have some special properties that come up, right? Before we talk about the parallel version, let's just talk about any 2 lines that are cut by a transversal. The angles in the top left corner are both in the same relative position at the intersection. Now, we know that these angles aren't in the same position, right? 1 and 5 are not in the same spot, because they were, we know what would happen, right? You remember the spooky video we watched, right? They were in the same position. Yeah, you don't want to be in the same position. But relative's okay. 1 and 5 are in the same relative position. What do we call angles that are in the same relative position? Corresponding. Starts with a C, because remember the cap? That poor kid. Corresponding. Now, corresponding angles are in the same relative position. If these two lines are parallel, then corresponding angles will always be congruent by corresponding angles postulate. Remember cap? So we know that these two angles, like 1 and 5, are corresponding angles. And since these guys are parallel, corresponding angles postulate says they are congruent. Yes, ma'am.
Were we supposed to draw a picture?
This is worth it.
Show the class, show the class.
This is worth it.
You really do.
All right, for those of you following along at home, I asked them to draw a picture, and I said, draw this right afterwards. But all she heard was draw a picture. So this is what we got.
Oh my gosh.
And she's wondering, like, that doesn't look like mine. Like, I wonder how that's going to work. Is it going to be like a magic trick where any picture...
Using these will have to have a parallel line.
That's beautiful. Can you, like, finish this and make it nice and put it up in the back there? We made some points of it. That was an amazing moment. Kozovic, you're a legend. Wow. Song of the day, donated to you. Or not donated, dedicated to you. I've changed my mind. I got too many people I'm dedicating it to today. All right, corresponding angles postulate. Okay? Let's talk about other types of angles. First of all, let's establish what I'm talking about when we're talking about location, location, location. Okay? This is the interior. I call it the interior because it's between the parallel lines, right? You dig? That's the interior. Now, if we have an interior, we must have an exterior. And you're right, we do. We do have an exterior. This is the exterior. It's the outside, right?
Okay.
Between here and here is the exterior.
That's a big guy.
Between here and here is the interior. And then, of course, further out is the exterior as well, right? Okay. So, I want to know two angles. Name me two angles that are in the interior. Go ahead. Katie Younger, give me two angles that are in the interior. 8 and 6 are not both in the interior. I know what you're thinking.
No, I wrote them
Oh,
out.
you didn't write the numbers like mine? It's okay. All right, Katie is currently fixing her numbers. Numbers are hard. Thomas?
3 and 4.
3 and 4, very good. They're both in the interior. Give me another set of interior angles. Yes, 5 and 6. You don't mind, right? Okay, give me an example of exterior angles. Hannah. Exterior angles, 1 and 2. Good job. Yay! Yeah, all right. Woo! Okay, good. All right, so now we know what interior and exterior means. Very good class. All right, there's another way to classify these because there's a left side of the transversal and a right side of the transversal. If they're on the same side, we call them same side or consecutive. Okay? If they're on different sides, we call them opposite, also known as alternate or alternating. Okay? So 1 and 4 are same side angles because they're on the same dumb side. 1 and 3 are not on the same sides. They're on alternate sides. We call them alternate angles. Okay? Give me an example of alternate angles, Mr. Brainerd. You know I'm going to call on you, right? Like a lot. And as long as you can handle it, I'm cool. Right? Okay. I mean, like, I'm not trying to be mean. I'm just, like, being fair.
Copying stuff down.
So, yeah, I know. So, like, give me an example of alternate angles. Different sides of the transversal. Like angle 1 and what?
Angle 2.
Yeah, they're on all opposite sides, right? So they're alternate sides. Yeah, nice, right? Ain't no thing. What about same sides? Give me same sides. McKenna.
No.
2 angles.
1 4.
1 and 4 are on the same side. Very good. She was ready, but she's like, if he calls on me, I'm gonna say that, but I hope he doesn't. I did, and I saw right through you. All right, so there we go. So let's talk about a combination of those two things, right? What happens when we're talking about interior and alternate? So, alternate interior angles. There's a theorem behind this. That's why I did it in blue. We're going to talk about that later. You can kind of think about, conjecture of what that theorem might be. Give me an example of angles that are alternate, meaning opposite sides, and interior. Rosie. They're in the interior and they're alternate. So give me an angle that's in the interior. 5 and 3. Yep, alternate interior angles. 5 and 3. So 5 and 3 are alternate interior angles. What about 4 and 6? Oh yeah, and they go together. Yes.
Do you consider it, is it on a different, like, would you consider 3 and 6 on different sides even though, like, you know what I mean? It's on the top, it's on the bottom, or not?
Nope. It's different sides of the transversal. Okay? They're both on the right side, so they're on the same side. All right, so we did alternate interior angles. Let's do exterior, alternate exterior angles. So alternate means opposite sides, right? Exterior means outside. Alternate exterior angles. Give me an example of those. Lorley, I need something that's alternate and exterior. Yeah, 1 and 3? Okay. Well, one of those is in the exterior, but the other's in the interior. So let's start with 1. Give me another exterior angle that's alternate. We have options. Those are on the same side. Yeah, she got it. The reason she didn't get it is because she forgot that this is also the exterior. And she's thinking like, well, it's not 2, right? Maybe 3? There's an exterior down here as well, so 1 and 7. Alternate, opposite sides, exterior. Okay? Cool. So 1 and 7 go together the same way, 2 and 8 go together. Now, technically, 1 and 2 are alternate exterior. They're on opposite sides. They're both on the exterior. But we don't talk about those in that way because there's a special name for angle 1 and angle 2. They're not corresponding. 2 angles on a line. Linear pair. Collinear means we can have many angles on a line, which isn't as special as just having 2, because if 2 angles are collinear, we know by linear pair theorem they must be supplementary, right? All right, we've done both of the alternate angles. Let's do the same side. Same side interior first. Give me an example of same side interior angles. Haley, same side and on the interior. Very good. And also 3 and 6, right? Cool. Now let's do same side exterior. Caden, give me an example of same side exterior. 1 and 8. Same side exterior angles. Very good. Now, I already alluded to this, but we do not call angles same side interior, same side interior. 4 and 3, same side interior. They are on the same, 4 and 5 are same side interior. We do call them that. My bad. What I'm trying to say here is that angles 3 and 4 are a linear pair, right? And that is what they is. That's the only thing they are to each other. 4 and 6 are not a linear pair. They're alternate interior angles because they're in the inside and they're alternate sides, right? Cool. Linear pairs add up to 180. These guys are actually by alternate interior angles theorem when we get to it are going to be congruent. Only when the lines are parallel, though. So, additional angle classifications, we have linear pair, which we talked about, right? And we also have vertical angles. Anybody remember vertical angles?
No. Yeah, I do. 1 and 3.
Where did they go? Vertical angles, yes.
Oh, scissors.
Scissor theorem, that's right. So scissor theorem, right? Your words, not mine, says that whenever 2 lines intersect, no matter how they intersect, right? The top 2 angles are going to be the same. The side angles are going to be the same.
Yes.
Vertical angles. It's because the angles scissor each other. That's what you said. All right, so we also have vertical angles. Hang on to this. Tomorrow we're going to talk about all the different theorems that come along with this, and they all stem from corresponding angles postulate. That's the beginning of it all. Okay?
Are we done with class A?
Not yet. Ladies and gentlemen.
Curry range.
Nice.
Oh, did I just sit down?
Buckets. No, you got it. You got it in the recycling. You're good.
All right, we're good.
All right. So, hang on to this. We might play a game on Wednesday with it. Okay? So if you're like Haley and didn't make one, you can make one now. We will have a quiz Friday. It'll be the last quiz of the quarter. If you need to make up a quiz or a test or all of them, you need to come see me.
That's scary.
Yeah, I do.
It's time.
I try to come see you in the room and I just get
Homeroom is not a good time for crunch time. If you're like, I need to get this done this week, which all y'all do, don't see me in homeroom. Do that and see me before or after school. Okay?
So is this quiz,
Come on into homeroom.
Is this quiz going on this quarter or next
This quarter.
Really?
Really?
That's a good thing.
How though?
What do you mean how? Grades are due next week.
Oh, really?
Yeah, it's probably a good thing too, because the people watching your grades gonna go.
I'm gonna be absent today.
Mr. Mack, I'm going home.
You have
She'll be
passed?
on. You don't have
I have no idea what you just said. What?
Yes.
Yes, you can. Who needs a pass because they need to make stuff up?
What are we? What
my
are we?
basketball.
Carpenter's the only brave one. All
I
right.
also need you to send an email to Mr. Gilma saying that I was in here the day that you left.
I got 59.
What day was the funeral or the day that you left early?
Okay, I'll tell him. Yeah.
Yeah, just send an email.
Friday. Friday? No, it wasn't Friday.
I think it'd be great.
Thursday.
That doesn't even. Yeah, she does, actually. Yeah, she throws Marlboro Reds.
Oh, God, I forgot.
You in a bit of trouble?
Huh?
In a bit of trouble?
Am I in a bit of trouble?
No, that's what I need to email.
Oh, God.
Oh, no, I didn't bring Duncan a pass, like Wednesday.